ஸோ இந்த செஷன் வந்து ப்ரொஃபஸர் ஸ்ரீஹரி கோபாலகிருஷ்ணா அவர்கள் வந்து நடத்த போகிறாங்க. அவர் வந்து நம்ம ஐஎம்எஸ்சியில் ப்ரொஃபஸராக ஒர்க் பண்ணுறாரு. அவர் ஃபிசிக்ஸில் நிறையா துறைகளில் ரிசர்ச் பண்ணிகிட்ருக்காரு. இதில் பார்ட்டிக்கல் ஃபிசிக்ஸும் அவரோட ரிசர்ச் இன்ட்ரெஸ்ட்டில் ஒன்று. இன்றைக்கி உங்கள்கிட்ட பார்ட்டிக்கல் ஃபிசிக்ஸ் பற்றி சில விஷயங்கள் வந்து எளிமையாக பேசுவார்.
வணக்கம் எல்லாருக்கும். இப்போ நாங்கள் வந்து வில் talk a little bit about particle physics, glimpse into the world of particles. எனக்கு தமிழில் கொஞ்சம் தெரியும், but I am not very fluent. Technical terms all I am not aware. So hopefully we'll manage. இங்கிலீஷ்னா புரியுமா? நான் இப்படி பேசினா ஓகேயா? ஓகே, வெரி குட். ஸோ ஏதாவது உங்களுக்கு டவுட் இருந்தால் கை மேலே தூக்குங்க. கேட்டால் நீங்கள் பிரச்சனை கேட்டால் வில் ட்ரை டு ஆன்சர். So don't hesitate to ask questions anytime something doesn't make sense. Raise your hand. We'll try to see a little bit about the world of particles. So everybody here hopefully is familiar with the constituents of matter. நீங்க இந்த protons, neutrons அதெல்லாம் படிச்சிருக்கீங்களா உங்க கிளாஸ்ல? ஓகே, வேற என்ன இருக்கு? ஆட்டம் எடுத்தா வேற என்ன இருக்கு? ஆட்டம்னா என்ன தமிழ்ல என்ன சொல்றோம்? அணு. அணுல என்ன இருக்கு? Protons, neutrons, electron, correct? And orbits, correct. Electrons in orbits. So அதுதான் நான் இங்க எழுதிருக்கேன். Protons, neutrons, electrons. அந்த bracketல என்ன இருக்கு? Quarks. அது கேள்விப்பட்டிருக்கீங்களா நீங்க? Quarks, right? Quarks are building blocks of protons and neutrons. Right? If you take a proton, break it up, you will find quarks inside. And how about electron? Does anybody know if you break up an electron, what might be there? No? Nobody has heard of what is inside an electron? That's because we have not managed to find what is inside an electron, right? As far as we can tell, electron is a fundamental object. But we have managed to break apart protons and find the quarks inside that. That has happened over the last 30, 40 years. We have been able to break apart a proton or a neutron, and we understand today that there are quarks inside. So we'll talk a bit about that, and also I'll talk a little bit about unstable particles. Do you know what unstable particle means? What does unstable mean? Huh? Half pulled electron. What was that? Half pulled. Okay, some particle which exists for some time and after a while goes away. Unstable na English word unstable. It's not stable. இப்போ டேபிள்ல 3 கால்ல டேபிள் வச்சா எப்படி ஆகும்? It's not stable, right? It will fall off, right? Same way here a particle can be unstable. We produce it somehow and we place it. After a while it may not be there. It may just go away. We know of many such particles. And I'll tell you about muon. Muon is one example of an unstable particle. We call it unstable because it's not a stable particle. It doesn't live for a long time. You produce it somehow and then it goes away into something else. So we'll see what that is about. Special relativity you have heard, right? Who wrote down special relativity? Which famous scientist wrote down special relativity? Anybody? Einstein. Somebody has heard of it, right? So it's usually called Einstein's theory of special relativity. So we will talk a little bit about that. Some things related to particles, how it is very, very important to keep track of special relativity in particles. Because the particles are very tiny, right? If you take a small amount of hydrogen gas, right? Even so much of hydrogen gas or air. We have air molecules, right? Do you know roughly how many atoms there might be in this chunk of air? Any guesses? 100 atoms? 1000 atoms? No? How many? millions, correct, millions, billions, trillions. Even if you take some small chunk of this material, there are usually around 10 to the 23 atoms in this thing. Power notation theriyuma ellarkum? 10 to the 2 ana 100, 10 to the 3 ana 1000, 10 to the 4 10,000, 10 to the 6 is million, 10 to the 9 is billion. இப்படியே பாயிண்ட் இருக்கலாம். 10 to the 23 ana, it's a humongous number, right? Really big number. 1 followed by 23 zeros, right? Insanely big number. If you take any amount of material, even a small piece of this thing, there are roughly around 10 to the 23 atoms in there. The protons, neutrons we are talking about are so tiny. You pack a lot of them together, and then you will get some material. So the point is, these particles are very, 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 very tiny, and they will feel very different world around them than what we are used to. So that world is the world of special relativity. So it is all very different. It's not like our everyday speeds. It's not like looking at a car moving, right? They will see other things in a very different way. We'll see a little bit about what those different ways are. And finally, I'll say a little bit about our understanding right now about all of these particles. And that's called the standard model. So that is what we'll do over the next half an hour. Yeah? Okay, let's get into it. So this we talked about, right? So structure of matter, you can see here atom. Scale is 10 to the minus 8 centimeter, right? Very tiny. So it says you take 1 centimeter, that is so much, right? And you break it up into 100 million pieces. That's a lot of pieces, right? Each piece will be the size of one atom, right? It's a very, very, very tiny object. And so then inside that, if you zoom, you take the nucleus, which is the center, you zoom into that. That is what is shown as nucleus. And that's around 10 to the minus 12 centimeter. So that's, you take 1 centimeter, break it up into a trillion pieces, right? 10 to the 12 is trillion. Each proton or neutron is of that, roughly of that size. And you take a proton or a neutron, a nucleus, right? That is shown there. And its scale is around 10 to the minus 13 centimeter. You further break it up, you get a quark. That's the quark that I was talking about, right? Inside a proton or a neutron, you have this, what is shown in green here. Don't take the colors very seriously, it's just artist imagination, right? Some color, but the fundamental particles themselves don't have these colors or anything. So you get these quarks which are very, very tiny, 10 to the minus 16 centimeter. That's very tiny, right? And on the other side is shown the electron. As you said correctly, there are orbits, and then we have an electron going around orbit around the nucleus, right? So that's the structure of the atom we are familiar with. Hopefully you have studied that in your school. So we'll take it off from there and go further and ask what might be the nature of these fundamental particles that is there to the right. So let's take the example of proton or neutron. So proton has charge +1, right? You know that. Neutron has charge 0, electromagnetic 0. It's neutral, right? And so that is what I put down there. And a mass of a proton I have given in kg. 10 to the minus 27 kgs, right? It's very, very, very tiny mass. You know 1 kg, right? If you take 1 kg of rice or something, you know, it's like so much of rice. And each proton is 10 to the minus 27 kg, right? And so if you take 10 to the 27 of these, you might get 1 kg of rice, let's say, right? 10 to the 27. Humongous number, right? So each proton, very, very tiny mass. So I keep stressing that you have to keep in mind that we are dealing with objects which are very, very, very small. And so how they behave could be very different than what we are used to, right? And we will see sometimes they behave very differently. So electron charge -1, everybody knows that, right? Electromagnetic charge, -1 for electron. And electron mass, I have shown it in different units. If you யூனிட்ஸ் ஆனால் தெரியுமா? நல்லா இருக்கும். Kilogram is a unit. It's a unit of mass. Correct. So unit of length is meter. Unit of time? Second. Right? So instead of measuring it in kgs, because it will be such a small number, every time I have to keep writing 10 to the minus 27 and all that, right? It's painful. So to just make life simpler for ourselves, we can define a unit which I have called MeV. That's a different unit of mass, right? And so I will say, if anytime you find 10 to the minus 27 kg, call that as 1000 MeV, roughly, right? 938, close to 1000. So say it is 1000 MeV, right? It's a different unit of mass. So I can measure things in units of MeV, measure the mass in units of MeV. So that is what I have done for the electron. Instead of saying that it is 0.51 times 10 to the minus 30 kgs or something, I have just said it is 0.5 MeV, half an MeV. Much easier to deal with number like half, right? Which is why we usually work in particle physics in units of MeV, which is a unit of mass. So we don't have to keep writing very small numbers, 10 to the minus 27, 10 to the 30, minus 30 and so on. Is that clear? Should I say once more about MeV? No? It's okay, right? Okay, very good. So that is about mass. So anytime I show the mass of some particle, I will use the units of MeV. You can always transfer it to units of kg by just multiplying by, if it is 1 MeV, I multiply by 10 to the minus 30 kg or something roughly, right? It's about that order. Another thing I've shown is something called spin. So it looks to us as though these fundamental particles, neutrons, protons, electrons, all of them, it seems like they are like spinning. That's what is shown here. Yeah, you have heard of it? Very good. So yeah, very good. So spin, in some units, we say it is half. That is again choice of units, right? In some way of measuring, this is all following quantum mechanics. Have you heard of quantum mechanics? Yeah. So in quantum mechanics, we have a notion or concept where spin cannot take any value, like a top. Top can spin with any speed, right? Any rotational speed. Whereas fundamental particles cannot spin with some random speed. They have to come with specific spins, right? That is what quantum mechanics tells you. And it is found that electron, proton, neutron, they all have spin half. They all spin like with 1/2 unit of spin. That is something that you can keep in mind. And it is also like a tiny magnet. Every subatomic particle is like a tiny magnet. Anytime you have a spin and you have electromagnetic charge, you can have something called a magnetic moment, which is shown there, which is like a tiny magnet. It's like a bar magnet on the fridge, right? It will stick. And why does a big magnet have magnetism? It's because it is made up of these tiny magnets. All the small protons, neutrons, electrons, everything is contributing. They all add up to get you a magnet, right? It's like each subatomic particle is like a tiny magnet. So these are some aspects of the particles that we know. Protons, neutrons, electrons. They are like tiny magnets and they have spin. It's like they're spinning and their mass is given. They're very, very tiny. So that's something which, if you didn't know, you can appreciate. But they're very small and they have these attributes. They have some charge and all of that. So any questions about this one? Okay, very good. So let's keep going. So how about antiparticles? Have you heard about antiparticles? Antiparticles na Tamil enna yarakavadhu theriyuma? Antiparticle. No? Anybody? No? Okay, I'll just explain in English and hopefully you will get, huh? antiparticle? Huh? Negative positive is one aspect, but not exactly, because proton is positive, electron is negative. That does not mean that they are antiparticles. They are both particles. So I will just say here that for every particle that we know of electron, proton, neutron, we know all of these, right? They are particles. So for each one of these particles, they have their corresponding antiparticles, and as you are saying, they have opposite charge. So electron has negative charge, so its antiparticle has positive charge. It's called a positron. Anybody heard of positron? இது பெட் ஸ்கேன் கேள்விப்பட்டிருக்கீங்களா? இப்போ ஹாஸ்பிட்டலில் போனால் ஸ்கேனர் இதில் இருக்குது, பெட் ஸ்கேன்னு சொல்லுவாங்க. மெடிக்கல் ஃபீல்டில் இட் இஸ் வெரி காமன் டு ஃபைண்ட் பெட் ஸ்கேன். பெட் ஸ்கேன் என்ன? பி அது பாசிட்ரான். It is called positron emission tomography, right? That is PET. That is because they give you a small dose of a radioactive substance which decays to, which produces positrons. And they use that to image the human body. They can see how your health is. They can see if there is anything that needs to be fixed. They can find out if there are any problems in the body. To look inside, you can use positrons. So check out, ask somebody, when you have a PET scan, what is that positron? That's nothing but this antiparticle of the electron that I'm talking about. Every way it is identical to the electron, except that, as you're saying, all charge is opposites. If electron has negative charge, positron has positive charge. Proton has positive charge. Antiproton has what charge? -1, right? So it's very easy. Neutron has 0 charge. Antineutron has 0 charge, right? So it's very easy. So for every particle we now have found in laboratories that you can make their antiparticles. We have confirmed this again and again and again. For every particle that we know, you can produce antiparticles. So that's a rule of the world. It's a rule of nature, that every particle must be accompanied by its antiparticle. And so what happens when one particle meets an antiparticle? That's what this diagram A is showing. What is on the right? That is light. So two particles come in from the left. One is positron and the other is electron, right? +1 is positron, minus is electron. When they come and meet, they go away. They form pure light. So that is another aspect which is always true. If one particle meets its antiparticle, then they both annihilate. We call it annihilate. And then it goes into photons. Light, same name for photons, right? Photon, light, same name. And so that is another aspect of the subatomic world, that everything has its antiparticle, and when particle meets antiparticle, they go to light or photons. Same way you can take two photons, shoot them at each other. If they have sufficient energy, you can create a positron-electron pair, or you can create a proton-antiproton pair. That's called pair creation. So that is also something that we have done in the lab. So this one, have you heard of E = mc²?
Yes, sir.
Yeah? So this one is demonstrating that. So on the left is just energy, right? Electromagnetic energy. And you can produce matter, the mass, by E = mc². You just apply that thing, whatever energy you have on the left side, you can get mass on the right side. Because electron and positron both have mass. Anybody remembers what is the mass of the electron? 0.5 MeV, right? 0.5 MeV. Use those units, lot easier. Otherwise you have to say 10 to the -27 and all that. By the time you say 10 to the -27 and all, she would have already shouted 0.5, right? So MeV is a very good unit. So electron mass 0.5 MeV. So if you have two photons coming in with at least 0.5 MeV each, then you can produce electron and positron by E = mc². So that's what this is saying. So it's a very general rule that we have particles and antiparticles in the subatomic world. And they are being created, they are being destroyed. Yeah? Okay. Any questions on this one? Yeah.
How can we use the MEV in our calculations?
If you want to compute what is the mass of 10 to the 27 electrons, right, you might find it easier to work in MeV units, or you might find it easier in kilogram unit. So if I tell you already 10 to the 27 electrons, right, or 10 to the 27 protons, let's say, it's easy to use 10 to the minus 27 because you will get 1 kg, right? 10 to the minus 27 into 10 to the 27 kilograms, right? That will be 1. So it is much easier to use the kilograms there. But if I'm going to do things with 1 proton, right, then it is much easier to work in MeV units. I can ask how much of energy is produced when 1 proton meets 1 antiproton. One is 1 MeV of mass and the other is, 1000 MeV of mass and the other is 1000 MeV of mass. So I have 2000 MeV of energy on the right hand side. So in that sense, when I talk in terms of photons, much easier to use MeV. That's one simple example, but simply because the numbers come out much smaller, easier to work with, 0.1000 and 0.5 and things like that. That's the only reason to use those units. Otherwise, there is nothing. You can either do the calculation in kilograms or in MeV. It will give you exactly the same answer, right? Any other questions? Yeah. It's okay. You can sit down and ask. It's fine. Or whatever you're comfortable.
We can create antiparticles for every particle.
Yeah.
Then what was the process for that?
Very nice. So one thing you could do is take 2 light beams, 2 laser beams with sufficient energy, aim it at each other, right? And then you keep watching. Sometime when they exactly collide with each other, you will find that positron electron pair gets created. So they'll come out and they will just go happily, right? So that's the process which has been used in the lab many times. Or you take an electron and a positron, shoot it at each other, right? You will produce light, right? And that has also been seen. So you can either take 2 photons, get electron, positron, or you start with electron, positron, get 2 photons. They have all been seen in the lab. So that's one way you can do it. Any other questions? Way back there. Sorry, yeah.
Is positron takes part in any of the reactions?
Yeah, like PET scan I told you, right? That positron that's emitted inside when they give the drug goes and finds another electron somewhere. And then it will do that process. It will do E plus, E minus goes to 2 photons. And the 2 photons come flying out. And that whole detector that they have in the hospital will just record those 2 photons and then it will reconstruct what is the tumor inside, what is the nature of the tumor, all of that.
Thank
so
you.
You can use that for imaging. Good question. Let's check out what is PET scan, what does it do? Sorry, question?
What is the full form of the
I didn't say that. Good question. It stands for million electron volts. I don't have the time to explain to you exactly why it is called that, but there is a reason why we call it MeV. But for now, just think of it as another unit of mass. And if you have the time later on, I can explain to you why the million electron. Million is easy to explain, right? It is 10 to the 6 electron volts. To tell you what is electron volt, I need slightly more time. At least I need 5 minutes. So we'll do that later. Okay, let's move on. So I told you about unstable particles. Let's see where we can find them. What is the notion of these unstable particles? One thing I already told you is unstable means that it exists for some time and then goes away, right? So one example that we have found are what are called as muons. What is a muon? It is exactly like an electron. Yeah? What do I mean by that? It has, I have not shown it here, I think. Exactly like electron means it has -1 charge, right? And otherwise it is much heavier. It's not like the electron because it is very, very heavy. It is 207 times more massive than the electron. So electron was half MeV mass. The muon is about 103.5, something like that, or 105 MeV or something. Have I put it down there? Yeah, 105.65, right? It's much, much heavier, 207 times heavier than the electron. So, right? Otherwise, it looks exactly like the electron. It does all of the things that electrons do. The other big difference is it is unstable. Now, we know what is unstable, right? When we keep it for some time, it will be there, but suddenly, poof, it disappears, right? It goes into other particles. And how long does it live? Anybody can read that. The tau is a lifetime. Minus 10 to the minus 6 seconds. Is that a long period of time, short period of time? What do you? Short period, right? Very, very short period. Millionth of a second, right, is 10 to the minus 6. Right? If I take 1, 2, 3, 4, that's all 1 second, right? In that interval, if I split it up into a million time intervals, very, very tiny instant of time, the muon will be gone by that time. You produce it within a millionth of a second, it is gone. In fact, it is 0.2. It is 1/10 of a millionth of a second. It is even shorter, right? So that is the nature of subatomic particles. We produce subatomic particles, and within a very brief instant of time, they're gone. And what does it go to? I have not shown it here, but let me just write it here. So a muon, so let me write it. It's denoted by this mu symbol. This is a muon. And if I watch it, it will, it will go to 3 particles, one of which is an electron. So mu minus I put here, and then it, after a millionth of a second, it's gone. 3 particles come out in its place. One of them is an electron. The others are what are called neutrinos. Yeah? So that's what a muon will do. These are unstable particles. You place it somewhere, after a while it goes away into something else. And we have seen that in what are called as cosmic ray showers. What is shown there is an example of a cosmic ray shower. You can tell that it is happening in the sky, right? Have you heard of cosmic rays? They are coming from somewhere, right? Outer space, from some other galaxy or something. They are coming and hitting our atmosphere. And they are very, very energetic particles. When they hit some molecule in the atmosphere, they can produce other particles, which is all shown here. They can, what is shown as pi there is a pion. So it has produced 2 pions and then one N, which is I think a nucleon. And that goes further and hits another molecule, new particles get produced. This whole thing is called a cosmic ray shower. That primary particle produces many, many, many hundreds of particles, in fact, of other particles. I think we lost the mic. Is it okay? So that is what is shown in the diagram here. And if you see at the bottom, ground level, there is that mu there, right? So that muon is what we can actually measure. We can put detectors on the surface of the Earth. There are many, 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 many experiments that are doing that all over the globe, where we put detectors on the surface of the Earth, and we can see that muons are going through. And we can study the muons by that. And in some of them will decay like this in our detector. So we can learn that, okay, this is an unstable particle, it has decayed. We can learn about all of these things. And that we have done for a long time in many experiments. And that's what is shown here. But the Earth's atmosphere is about 100 kilometers thick, right? But I told you these muons live for only about a millionth of a second, right? Is it possible that some muon hit some particle hit an air molecule and produced a muon, right, as is shown in that picture? Can you see it from the back? Maybe I should draw bigger. So some muon got produced, and we are here. Surface of the Earth is here, right? We have put our detector here, and if this muon comes through, we can detect it. But can it go for 100 kilometers? I told you many experiments have measured it on the surface of the Earth. But can it go 100 kilometers? No. Why not? Millionth of a second. So what should I do? So the lifetime is of the order of 10 to the minus 6 second, and the length it has to go is 100 kilometers, right? And so I can compute if it is even traveling at the speed of light, right? You know speed of light, right? Three into 10 to the 8 meters per second, right? So if I want to compute in the lifetime, in 10 to the minus 6 seconds, how much distance does it go, right? That's easy. I can just do c times this time, right? That will give me the distance that it has traveled. Velocity times time is the distance, right? So I can just plug in the numbers now. C is 3 into 10 to the 8 meters per second into 10 to the minus 6 second, which will give me what? Very nice. Meter, right? That is if it is going at the speed of light. 300 meters, which is 0.3 kilometer. So before it goes away, a muon can can go only 0.3 kilometer. But this thing is 100 kilometers. It got produced there. How is it traveling 100 kilometers? Puzzle, right? It should not happen. All the muons should have gone away by the time it reaches the surface of the Earth, because they don't live for that long. So the puzzle is answered by special relativity. And it's a beautiful demonstration that we can see in everyday life. You can put a detector, and the way you understand this is in special relativity. That's what is shown here. And it is called time dilation. So I think I'm way out of time. I cannot derive to you this formula, so I'll just state this formula. So if you see that delta t, what is it saying? So it is simply trying to say that if I have a moving clock, I am on the Earth, I have a stationary clock, right? Clock, we all know the clock, right? So I am measuring the clock. I say that, okay, there is a clock which I can attach to the muon. It is a thought experiment, right? Muon is very, very tiny. I cannot attach a real clock to it, but I can imagine that there is a tiny clock which is carried by the muon, and it is measuring its time. And it will say, okay, after 0.2 microseconds, okay, you better decay, right? It is a clock in the frame of the muon. Now we want to ask an Earth clock, what is the time? And the formula that is saying there is that those two are not the same. One of the big revelations, or one of the big things that special relativity tells us, is that clocks the way the clocks tick are not the same. It is observer dependent. If there is a moving clock, it goes at a different rate. The ticking, right, is different for a moving clock versus a stationary clock. If you don't take into account, you run into this paradox. But you allow for the fact that clocks go differently, what is 0.2 microseconds in this clock in the muon frame is much, much longer for us, right? It can even reach whatever is the time needed for that muon to go all the way 100 kilometers. You can compute what is the time needed, right? Time is, if it is almost going at the velocity of light, right, the time needed is c. How do I compute this? It should be 1 by c, right, and 100 kilometers. This is 10 to the 5 meters by 3 into 10 to the 8 meters per second. So I'll get something like 1/3 10 to the minus 3 second, right? So it should live for at least 1/3 of a millisecond, right? What appears like a microsecond in this clock will appear easily like a millisecond in this clock. And that's what that formula is relating. How do you compute from one clock to another clock? So I don't have time to explain to you in more detail what that is saying, but that is roughly the idea, that clocks run differently whether it is stationary or moving. That's what Einstein worked out. That's called special theory of relativity. Time is also relative. Before that, it was believed that time is running the same for everybody, whether they're stationary or moving. But special relativity tells us that is not the case. And when you account for that fact, this puzzle goes away, because the clocks run differently. Even though this is measuring 0.2 microsecond, in an Earth clock, we will easily measure something like a millisecond, and it will live for millisecond, no problem, because it is traveling almost close to the speed of light. It's going very, very fast. We don't notice it because in our everyday life, we never see objects which are moving that fast, right? We only see cars which are moving at 100 kilometers per hour, or maybe planes which are going, like, I don't know, 1,000 kilometers per second or something, right? Per hour maybe. You can find out how fast a plane moves. So those are very small compared to the speed of light. So you don't notice all these effects. But when particles start moving close to the speed of light, this effect becomes very, very big. Yeah? So that is the basics of how we understand these kinds of puzzles. Another thing also is length contraction. How do you, like what moving measuring rods, how do they appear when they are moving? They appear contracted. If it is at rest, we measure one length. If it is moving, it looks like it is shorter. And that is also one fundamental aspect in special relativity, that clocks slow down, moving clocks slow down, and moving lengths contract. And those are all aspects of the subatomic world, because they are all moving very fast. They are very tiny. They easily reach the speed of light, almost. But nothing can cross the speed of light, right? That's another thing special relativity says, that nothing can go faster than the speed of light. The maximum you can do is get closer and closer and closer to the speed of light, but never attain it. Okay, any questions about this? Okay. So I will more or less end by giving you this picture, which gives us a summary of what are all the unstable particles we have found in nature. In various laboratories, we have found all of these particles, right? So you should recognize the first column, U, D, E, right? That U, D are the quarks that I was talking about. The proton and neutron are made up of the U and D quarks. They are stable. If you put them somewhere, they will be there forever. They don't go away into anything. If you put an electron, it will be there. It won't go away. Similarly, neutrinos, they are also there. The other ones, the C, S, T, B, mu, tau, all of them are unstable. You can produce it in the lab, but they'll go away. Yeah? So these are all particles that we have found in laboratories. And in cosmic ray showers, because they get produced, some of them can reach the surface of the Earth, we can measure them. Some of them not, like a muon reaches the surface of the Earth. But the other particles are very, very short-lived. They don't live for so long that they can traverse so much distance. So we have to measure them indirectly, which is what we have done in the lab. And the center is the Higgs boson that was recently found in 2012 at CERN in Europe. And the other one are the mediators of forces. So that is the photon which is shown there as gamma, the top right box. And that is a light particle, photon. There are other force carriers also, which is shown as Z, W, and G. And these are all particles that we have produced in the lab. So this is a complete picture, we think, of what all is out there in the subatomic world. Any questions about this? Okay. So this is one picture of the Higgs boson discovery, and in 2012 this is a gigantic machine which was used to produce the Higgs, proton-proton collision producing the Higgs and going to light particles. And on the right hand side is shown the two light particles that are coming out in this detector. They have detected these light particles, and we can tell that something was produced in the center of that thing, which is the Higgs. And doing such experiments, we have found all of those particles in the table earlier. So that's just summarizing how these things are done. Okay, I'm out of time, so let me end. So I showed you that particle table. That's the entire picture of what is out there in nature as far as we can tell today. So we have a pretty good understanding of what are all the fundamental particles in nature. Yeah? And then, but there are still big puzzles. It's not like we know everything. You might have heard of dark matter. So we don't know what dark matter is. We also don't know what happened to all the antimatter. We only see the matter in the universe, and we don't know where is the antimatter. So that is also a puzzle. Okay, I'll stop here. Are we out of time? Huh? Yeah, if we have time. Yeah.
உங்களுக்கு ஏதாவது கேள்வி இருந்தால் கேட்கலாம் இந்த செஷன் பற்றி, பார்ட்டிகிள் ஃபிசிக்ஸ் பற்றி எதுவும் கொஸ்டின்ஸ் இருந்தால் கேட்கலாம்.
Yes.
Sir, sometimes we use that spin as minus half, sir. When we will use that?
Spin is plus half.
But sometimes in chemistry we use minus half.
You use in minus half in chemistry
Yes,
sometimes?
sir, sometimes some.
You've already used plus and minus? Okay. So one way of saying is a spin can either point up or it can point down, right? If you measure this, you will get plus half. If you measure this, you will get minus half. That is one way of understanding. If I understood your question correctly, that's one way of answering. It has plus and minus. Yeah. Any other questions? No? Okay, very good.
Sir, how can we produce muons in laboratories? Is it possible, or we only get it in the space?
Excellent question. So it is very, very possible. So what we have done is, for instance, we have similar to that collider that I showed you. So this kind of a machine. We have also built machines where we take a positron and electron and collide. So here, what happens? There will be a light particles. And that light particle can then decay to mu plus, mu minus. So I started with E plus E minus, and I ended up with muons. So this I can then record and know that I have produced a muon. It's a very good question. Yeah, we can do all of the antiparticles in laboratories like that. Yeah.
So can you explain us about dark matter?
Okay. Can you give me 1 more hour? I can explain to you. It is a big story. I will. Hello. Please, quieten down.
கொஞ்ச நேரம் இது கவனிங்க.
Quiet, please. I cannot shout louder, so please. So dark matter is something which we see in cosmology experiments or astrophysics experiments. So it is there. If you take our galaxy, there is some amount of mass which we can infer by gravity. We know that there is some mass here, but we can also account for all of the stars and all that are out there, and there is not enough. We see much more gravity than we can account for in stars. So we keep doing this again and again, and in many measurements, we see the effects of gravity, but we don't know what is producing it. We can account for all of the known, the table that I showed you, right, all the particles. We account for all of them. We know how much there are in, of all of these known particles. We account for it, but we fall short. We don't seem to be able to say, why is there so much mass, right? So we take all of the things we can account for, all the stars, and whatever remains, we say there must be something. We don't know what it is. There must be something. We call it dark matter. So that's a short answer to your question. Yeah.
What does dark matter is made up of?
That is something we don't know. Very good question. We are trying to find out. Huge number of people are involved around the earth to find out what is the nature of dark matter. We keep doing experiments. We take this and we go deep in the mines and we build very sensitive detector, right? We take a big tank of something like xenon. We take xenon atoms, right? And we hope that some dark matter comes, collides with this, right? And we want to know if dark matter comes, collides with this one, will get pushed around. Can we measure that recoil? Can we record the deposition of energy and know that there is a dark matter particle that came and hit? So far we have not seen, but we keep trying. So many experiments are trying to find it. Yeah.
If there are any other particles in cosmic rays other than muons?
Very good question. So that thing shows many particles that are produced, right? So it is showing pions are produced, some neutrons and photons, electrons, positrons. Any particle, antiparticle can get produced there. In fact, something can get produced where it is a charm quark or something. But they are all very short-lived, and so they decay to other particles. I was focusing on muons because only muons reach the surface of the Earth. There are other particles, antiparticles that get produced, which decay very quickly because they're all very short-lived. They're extremely highly unstable. They get produced but decay.
You told that we can detect that we receive some muons from outer space, but is it possible to know where they come from, the source of those muons?
Very nice question. So, what is coming there is not a muon. What is coming there is some other particle. Many particles can come. In fact, that could be a proton. or it could be even an iron nucleus. So they come and hit the molecule of the atmosphere. And the secondary particles are muons. The primary particles could be any iron nucleus or proton or whatever, right? Something which comes from very far in, like from very far away in the galaxy, or sometimes even from neighboring galaxies and all that. And they can come and collide, and the product of it will be all of this. That primary thing shown as a white arrow could be something very different.
ஸோ ப்ரொஃபஸருக்கு நம்ம இந்த ஈவெண்ட் இந்த செஷன் எடுத்ததுக்கு தேங்க்ஸ் சொல்லிடுவோம்.